Hello, what's up, you scholars of enlightenment? Hope the sound is coming through okay. I'm just getting a little check on that. How are we looking on the sound? Anyone in the chat? How's the sound coming through? Excellent. Looks like we've got a go ahead on the sound. So what's up, you scholars of enlightenment? Something very interesting to muse on today. We're going to be talking about and watching a live stream of the latest results from Fermilab and the g-2 experiment. So I wanted to get on a little bit early. The results are coming out in about a quarter of an hour. But I wanted to do a little bit of a primer on what we're going to be watching, why we're going to be watching it, why it's interesting, for those who potentially don't know too much about it. So the Muon g-2 experiment, well, it's an experiment that had some difficult beginnings, getting funding first of all. Initially, it was set up at the Brookhaven National Laboratory in New York, and then it was moved all the way down to Illinois and is now based at Fermilab. So my friend Jason Stephan has some good stories about this, and if you go online you can see all these interesting photos of the thing being disassembled. Here's a nice picture of the g-2 experiment taken down the coast up the Mississippi because they couldn't disassemble this huge experiment, taken on the roads. It's a huge wide experiment which they can't take apart, so it was a hell of a trouble to move, and then finally being reinstalled up at Fermilab in Batavia, Illinois. And what this experiment does is it's looking at the magnetism of the muons. So if you have a little bit of familiarity with the standard model, or perhaps not, of particle physics, you're probably aware of the particle, the electron that whizzes around the atom. Now, the muon is a heavier cousin of the electron. It behaves very much like the electron, but it's heavier. And what the g-2 experiment looks to do is look at its magnetism, look at its magnetic moment, how it behaves in a magnetic field and the magnetic field that it generates. And we're looking to determine essentially the muon's magnetism, the muon's magnetic moment. That's what this experiment hopes to do in, hopefully, the pursuit of finding new particles. Now, how does it do that? Well, the Muon g-2 experiment measures the muon's magnetic moment, as we've said. How does it do that? Well, it moves particles around a 15-meter diameter track. If we can get a nice little picture of the experiment again, 15-meter diameter track with a strong magnetic field applied. And a powerful magnet keeps the muons on this circular track, and at the same time makes the magnetic north, so you can see these lines in the picture, these black lines, makes their magnetic norths precess or rotate around like a spinning top. And the rate of this precession, the rate of this spinning in a very well measured magnetic field in this experiment, can help us to determine how strong the magnetic moment of the muon is. If there's a stronger magnetic moment, we'd expect it to spin more quickly. If it's weaker, less quickly. And the previous results from the g-2 experiment caused a little bit of a buzz, and that's why there's a little bit more of a buzz today about the new set of results. So the original results were announced in 2001, and then they were cleaned up a little bit over the next sort of 5 years towards 2006. And what they found was that the muon's magnetic moment, which, as I've said, is a measure of the magnetic field it generates, is slightly bigger than what quantum physics would predict. So today, we're looking at the new results and seeing if that anomaly, that tension between the theory and the experiment, holds up with the new results. So what would we expect for this result? Well, to first approximation in quantum physics predicts that elementary particles like the muon, like the electron, should have a magnetic moment which is exactly 2 in units that depend on the particle. But a fuller calculation reveals that there's a bit of a deviation from this number of 2, this perfect number. And the reason for that is because the empty space around us, the vacuum around us, is not actually empty. It's not actually having nothing in it. It's not just empty space. There's actually particles, whether you can believe it or not, that are popping into and out of existence all the time. And these particles, called virtual particles, they interact with our muon and they change its magnetic moment. They have an impact on its magnetic moment as they appear, disappear, and interact with the muon. And the more of these different types of particles that exist, the more virtual particles that are popping into and out of existence, the bigger impact they will have, or the different impact they will have on the muon's magnetic moment. So when we're measuring that magnetic moment of the muon, we're essentially measuring how much stuff is popping into and out of existence in the vacuum. So if we have a big difference between the expected value of the muon's magnetic moment, taking into account all the particles we know of and all the effects that we know of, and we still have a big discrepancy, that suggests that there's new particles, new phenomena popping into and out of existence in the vacuum. So looking at the very exact value of g-2, the magnetic moment of the muon, can tell us indirectly that there's new physics, new particles popping into and out of existence in the vacuum. So it can't exactly tell us what they might be, but it can give us hints as to where to look and that these things exist, which is always nice to keep our dander up and keep us moving forward. It's been a busy time in particle physics. Recently, we've had LHCb finding new particles, LHCb's tension with the lepton universality and the decay of B quarks, and now this result this week. So some very interesting times in particle physics and some tensions that are coming with the standard model. So, as I said, we expect that value of the magnetic moment of the muon to be around 2. We'll look at this live stream, which is starting in 6 or 7 minutes, and we'll see if their results are significantly different from that. At Brookhaven, so the initial run of this experiment, g-2 found a value of 0.0023318,319. So a small deviation from essentially 2 or 0 once you've taken the 2 away, but nevertheless a result that was in tension with the particles that we know exist. And we're hoping today with this new data, well, personally, I'm hoping that the tension remains and we hopefully find some signposts for new physics and new particles. But we'll have to see if that tension and that direction of g-2 changing away from the expected value holds up. Now, what could it point to if there is a significant difference, a significant anomaly between the theoretically predicted value of the muon magnetic moment and the experimental value? Well, difficult to know because obviously this is not a direct measurement. It's just telling us there's something out there. But there are a few candidates. So as I said, we're talking about new particles, probably some odd particles interacting with the muon and changing its magnetic moment, perhaps some that we don't know about. Here are some that we do, things like neutrinos, things like photons, but could also be things like a second Higgs boson or some more exotic particles that we simply haven't thought of or which are a little bit more crazy in the theoretical scheme. So there's a lot of possibilities. The LHC has closed off quite a lot of the bigger candidates, potentially things like light SUSY particles. But things like a second Higgs, things that are more exotic, different theoretical frameworks could possibly explain this. So difficult to say until we get the results what would be the most likely reason for this. But as I say, if we find a significant tension, that's only going to fuel the flames and fuel the fires and get more people looking at this and get the theoreticians chomping at the bit. So lots of things it potentially could be. And just a little word of warning as we go into looking for a stream to watch these results live. The results are going to be unveiled today, but it might not be a settling to the issue. So, you know, a little disclaimer essentially. So the amount of data that we've got here should be about a 4-fold increase in accuracy on the previous results. But it might not be enough, depending on what the results are, of course, to be able to definitively say we've got a real discrepancy, a 5 sigma discrepancy, a bolt of lightning result that shows that the magnetic moment of the muon is very, very different and significantly different from the theoretical predictions. So we're hoping we get some absolutely bananas, amazing result, but we'll have to wait and see. So just a little disclaimer there that this might not be the final word. And in fact, it can't be exactly the final word, because if Fermilab ultimately confirms the original results, the Brookhaven surprises in the muon magnetic moment, us in the scientific community are obviously going to demand some independent verification. And that could come from another experimental technique being developed in Japan at the Japan Proton Accelerator Research Complex, the J-Park, near Tokai, where they're also looking to measure the magnetic moment of the muon in a radically different way, which I might follow up on in a video depending on the impact of these results. So might not be the final word today, but should be very interesting. And hopefully we'll get a little bit more tension between the standard model and the observations that we're getting. So let's go and try and find a stream to watch these results live, because that's a little bit of a primer, help you to understand exactly what's going on. If there's any questions that you'd like to ask before the stream starts, as I'm going and looking, please feel free in the chat. Thank you, George. Thank you, Sophie, for confirming that the sound is good. Yes, Antoine, we are going to watch the stream live. I was going to jump away now and try and find that stream from Fermilab, because I don't know if it's gone up on their live links yet. It is due at 4 o'clock, I believe. So there's a link to it here, the live stream, and it's supposed to start at 10 a.m. on the, I believe it's American Central Time. AM US Central Time, so 10 US Central Time, which I believe is about now. Be very embarrassing if I've obviously got the time wrong. Nope, should be a couple of minutes from now, so we'll just have to wait for that stream to get started, I guess. So any more questions? Very happy to field those while we're waiting a couple of minutes for this stream to start, so we don't have any or too much dead air. The link is already there, is it? You've got it. Well done. Thank you very much. Just come live, I think. So here we are. Thank you, Potato, for updating me of that. I've got about 15 screens open, trying to keep a hold on everything, watching the chat, trying to get the link open, looking at some other things, getting people to check that the sound's working okay. So I appreciate a little bit of help in the chat as ever. So some really nice pictures of Fermilab here in Batavia in Illinois. Here's the experiment being brought in. It was at Brookhaven, as you can probably see written on the side of the experiment. And it was moved as a whole up to Fermilab, Illinois, which meant they had to march it down the coast in a big boat, up the Mississippi in another big boat, and then stick it on a truck and very slowly bring it up to Fermilab. So a little bit of an undertaking. As I say, my friend Jason Steffen, who's a professor at Las Vegas University, has some great stories about it. And I think I'm going to have a chat with him tomorrow further about these results when they come out. But we'll get the stream first, if it holds stability. So a question from Antoine about some of the possible candidate particles. The one that I've seen discussed quite a lot is the potential of a second Higgs. Now, it seems like a lot of people, this isn't exactly my exact area of expertise in particle physics, but it seems a lot of people were also interested in it potentially being SUSY particles, so supersymmetric particles. Obviously, the LHC hasn't seen any evidence of those particles, so it's difficult to suggest that this might be SUSY. It could be some versions of SUSY, I believe, where they continuously tweak some of the parameters to make sure that SUSY never dies. My professor used to call it the theorist pension plan. But I believe one of the big candidates is potentially a second Higgs, and some other more exotic ones that I'll cover in a video, which I'm not particularly familiar with at the moment. But I'm excited to do a little bit of research about. I think 1,001 people are trying to connect to this live stream. So as soon as it gets a little bit more stable, we'll hopefully have this live stream for us to watch together. And while we're waiting for that, happy to answer any more questions you might have. Seems like we're still waiting for them to start the stream proper, when hopefully it'll be a little bit more stable. Sounds like they're having a little bit of a lag issue if we look at the comments. Question from Majestic Potato about what are your hopes, expectations for today's announcements. As a scientist, I guess I'm supposed to say, whatever the results will be, it'll be fine. Obviously, as a human being, I'm hoping there's going to be even more tension between that standard model,
Today, you're going to hear presentations.
Quantum prediction.
Today, you are going to hear presentations from two distinguished scientists about calculations and measurements of the muon's magnetic moment.
I'll come back to that question,
more than 6 decades. As time has marched forward, the precision, both experimental and theoretical, has continuously improved. The results you will hear about.
Okay, this is kind of generic, so I'll finish off answering Potato's question. So I'm hoping there's a big difference. And the reason I'm hoping that is I have friends in the field and I want to give them something to research. Obviously, I'm always excited to see new physics, new exciting physics. And we know the standard model can't be the last word in particle physics. It can't explain a lot of phenomena like dark matter, like gravity. So the more signs of new physics we can find, hopefully the better we'll be able to understand the universe. And if we find new physics here, hopefully it'll give us new places to start to look for even more new physics and a better understanding of the universe. So I'm hoping for tension, I'm hoping for chaos,
professor of physics
but we'll see what happens.
Illinois. Professor El Khadra is a theoretical physicist focusing on lattice gauge calculations. Over the last several years, she has served as the co-leader of the Muon g-2 theory initiative, a global effort to bring scientists from around the world to assemble
Our friend here very much reading off a script. I know what that looks like.
Once we know what we need to know about the theory, we will turn to Dr. Chris Pollard from Fermilab, senior scientist and co-spokesperson of the Muon g-2 experiment. Chris was a graduate.
So it looks like we're going to be getting another theoretical grounding from a professor at Fermilab telling us exactly why we're interested in this. And then we're going to march forward to the experimental results. So we're going to go from front to back.
So without further ado, let me pass the microphone to Professor El Khadra. Aida.
So we're going to hear a little bit more about the theory and why we should care about this result.
Thank you, Kevin, for this wonderful introduction. It is truly my pleasure to be here today for this very exciting event. My name is Aida El-Khadra, and I'm giving this presentation on behalf of the Muon g-2 Theory Initiative. And I speak on behalf of the Theory Initiative when I say that we are very, very grateful to be included in this wonderful event today. The Muon g-2 Theory Initiative
just happy to
has
be
as its goal to refine and understand the standard model theory that goes into the muons announced magnetic moment. For that purpose, in the last 4 years, we have held 6 workshops, and the first paper from the initiative came out last year and is the basis for the standard model prediction that I'm going to tell you about today. Our work continues, and we have a workshop planned, a virtual workshop.
So remember, there's a prediction about what this value should be. That's what we're going to get the theory on now, and then we'll get the experimental result and see if there's tension.
About the magnetic moment of elementary particles, such as the muon and the electron. These elementary particles carry intrinsic angular momentum, also called spin, which is an entirely quantum concept for an elementary particle that is point-like in nature. The other feature of these particles is that they carry electric charge. The muon, the electron, and the tau lepton, which are siblings, together with their spin, gives rise then for each of these particles to a magnetic moment that depends on charge, spin, and the particle's mass.
So they behave like little bar magnets
moment
in a simple
basically makes
way.
these particles act like teeny tiny subatomic dipoles, which will precess in a magnetic field, very much like a spinning top. And this precession can be measured very, very precisely, which is what Chris Pauly will be telling us about in just a minute. I'm going to focus on the theory prediction, which focuses on the coefficient G, also called the G factor. When Dirac put together an equation for the electron, and a relativistic equation for the electron, he found that the G factor was exactly equal to 2. In our quantum field theory language with Feynman diagrams, this corresponds to a muon interacting with the virtual photon from the magnetic field at a point. However, quantum fluctuations, quantum effects are ubiquitous in the quantum field theory, and these effects will have the effect of making the vertex, the point-like vertex, a lot more complicated. The first such correction was calculated by Julian Schwinger, and here's the Feynman diagram, which shows you how a muon will emit a virtual photon before it interacts with a magnetic field, and then reabsorb that virtual photon. This is the simplest of all the possible quantum
add tiny little extra bits on because they become smaller and smaller
magnetic
and smaller.
moment can undergo. And it resulted in a deviation of the G factor from 2 by a small amount, alpha over 2 pi. This is such an important result that it was engraved in Julian Schwinger's tombstone. Alpha here is the fine structure, which comes in at 1 over 137, and that is what makes this correction really small. So this invites us to define the anomalous magnetic moment, which is entirely due to these quantum corrections. So these quantum corrections, of course, change how the muon interacts with the magnetic field, and they can be calculated within the standard model of particle physics. All known particles contribute. All known particles are described in the standard model of particle physics, where you can see a graphic illustrating the standard model here. The standard model completes, the standard model was recently experimentally completed with the discovery of the Higgs boson, long predicted, and provides an extremely successful description of very many known particle physics experimental information. Here you see over here you see the charged leptons, the muon and its sibling, the much lighter electron and the much heavier tau lepton. And as illustrated here, these particles interact.
So all of these standard
the
model particles have an impact.
They also feel
on the magnetic
force,
moment of
so
the
they
muon.
also interact with W and Z bosons. And of course, all the particles in the standard model receive contributions from receive their mass from the Higgs boson. Now, the muon does not directly feel the strong force, but it can exchange virtual photons with the quarks because they also carry electric charge. The quarks that make up our regular matter, the nucleus inside the atoms of which we exist, are of course the up and down quarks, and they hadronize into the proton and the neutron. Now, the Standard Model, as beautiful as it is, it leaves quite a few questions unanswered. Why are there 3 generations? Why not 4? Is there in fact a 4th generation? What is the nature, the particle nature of the dark matter that has been observed? And what about dark energy? Why is there a lot more dark matter in the universe, a lot more matter in the universe than antimatter? Why is the Higgs boson mass coming in at 125 GeV? Answers to all of these questions generically lead, when we try to answer these questions with new theories, with new models, those generically lead to new particles that are not part of the Standard Model. If these new particles then can in turn contribute to the muon's anomalous magnetic moment via those quantum fluctuations, and if they do so significantly, Standard Model theory will disagree with experiment.
So if there are new particles out there that we don't know about,
particles may be very
they will change that magnetic moment of the muon,
fleeting,
and we'll be able
they
to
may be
know
very
they
heavy,
exist
so that they
by
have
them
not
having that
been
impact.
produced in high energy experiments. No matter their nature, they may show up in these quantum fluctuations in the anomalous magnetic moment, and hence a precision measurement provides us with a window with discovery potential for new physics. So another thing that is very interesting is that 20 years ago, the Brookhaven experiment, which performed a very precise measurement of the anomalous magnetic moment, found that it was disagreement at a tantalizing 3 to 4 standard deviations level with Standard Model expectations. In the intervening 20 years, Standard Model theory has been refined, and refining it further is the business of the Muon G-2 theory initiative based on the community's input. The Standard Model theory has been stable in that the errors have come down, but the overall central views have moved around a little bit, but not very much. And I will tell you about the status of the theory in just now.
So the theory prediction of this value hasn't changed very much,
receives
but we have this tension
from
with the old
quantum
experimental
electrodynamics,
value.
from the weak interactions, and also via the exchange of virtual photons with quarks from hadronic contributions. So here's an overview over this. The QED contributions, where I'm showing here the Schwinger diagram, that's the leading contribution, but this has been calculated to order alpha to the 5th power and is known very, very precisely. The weak contributions
so as time's gone by, we've got more
order
refined in our particle physics. We've been able to calculate
the difference
the magnetic
between
moment,
the weak
in
contributions.
theory,
They are very,
ever
very small
more
compared to the QED contributions.
efficiently and ever more
The
accurately.
hadronic contributions are classified in 2 contributions: the vacuum polarization, which is illustrated here. It starts at order alpha squared, so it is much smaller than the leading QED contributions. And here the muon emits a virtual photon, which then creates a quark-antiquark pair, which immediately hadronizes into lovely hadrons such as pions and kaons, etc., and resulting in a very complicated structure inside this blue hadronic bubble. And similarly for the light by light, there is a hadronic structure generated in this higher order diagram, which is suppressed by alpha cubed, so hence much smaller. If you look at the size of the contribution from the...
And difficult for the theorists to calculate because it's strong effects, things with quarks and such. So all of these contributions, just while we've got a little break here while it's buffering, all of these contributions are things that the theorists can calculate to come up with the theoretical value for the muon's magnetic moment. All of the different particles in the Standard Model contribute to it. So knowing more about those particles, having better calculation techniques, we can more accurately predict what we think the magnetic moment of the muon should be. So that's the theory here. We're telling you what the value should be.
Theory error arises due to the evaluation of these integrals directly. So this is what I will be telling you a little bit more about, because
so I think they're having a little trouble over at Fermilab because I've just done a speed test on my internet and it's fine. I guess a lot of people are connecting to this and it's slowing it down a little bit. I'll give you a little bit of more information on the slide then while we're just waiting for the buffering. So
refining the standard model theory prediction means that we need to refine the hadronic.
So essentially over the last 20 years since the result, we've got better at predicting what the value should be, but the value that we think the magnetic moment of the muon should have hasn't really moved around very much. So the whole point, if I was to sum up this slide, this presentation, would be that we still have that tension because that old experimental value is still 3.5 sigma away from our best theoretical predictions even now. Let's refresh this and see if we can get back up to speed.
Better.
It seems like they're having a little problem at Fermilab. Fermilab's IT is notoriously bad, apparently. I'm not going to say anything as a Cerny. I'll allow that one to go. A lot of people seem to be having trouble with the stream.
Theory error arises due to the evaluation of these integrals directly. So this is what I will be telling you a little bit more about, because refining the standard model theory prediction means that we need to refine the hadronic contributions. So why are they so difficult to calculate? Thermodynamics and the effects of it are very difficult to calculate directly.
So anything to do with electrons and photons and electrodynamics is quite easy to calculate because these alpha values get smaller and smaller and smaller. You get alpha, alpha squared, alpha cubed. And because alpha is a very small number, 1/137, these higher order, more complicated diagrams with lots of lines contribute less and less and less. The problem with the strong force, quantum chromodynamics, is that alpha value is greater than 1 often. So higher order diagrams contribute more and more and more. And it's very, very difficult to disentangle all of the contributions, all of the diagrams that could contribute to something like the anomalous magnetic moment of the muon. So calculating electromagnetic effects, electrons, muons, photons, is relatively simple because we only have to look at a couple of these Feynman diagrams. When we're talking about strong force effects, we have to look at loads of them, or make some experiments
are being analyzed and come online. The current uncertainty, the relative error on the HVP contribution comes in at about 0.6%. So it is a sub% uncertainty total, but that is not good enough for the precision needs of the Muon g-2 experiment at Fermilab. The light by light contribution, there is now a new dispersive approach that also allows for a data-driven evaluation using experimental data. All of this is a little bit more complicated. The current error is at 20%. It's almost completely quantified now, QCD. And so we now have a fully quantified evaluation of the hadronic light by light. Don't be alarmed by this 20%
so we
error.
Have a
we
good,
actually don't need
not
to know the light by light contribution as precisely as the hadronic vacuum polarization,
be. And
because
we're getting
it is
better
so
and
much
better
smaller.
And better
a 10% error,
but we still need to be
sufficient
better
for the precision needs.
Because
of
if
the
we have
experiment.
a difference between two results, but we don't know what our prediction, our flaw should be.
That is completely
how big is
independent
that
as
gap?
well, is a direct calculation using Euclidean lattice QCD. Here, one takes space-time and discretizes it and uses then the discrete and the finite volume integrals and throws them onto a big supercomputer. So the integrals that are otherwise really hard to evaluate on paper and pencil can now be evaluated on big supercomputers using Monte Carlo methods. This approach has inherent in it some approximation, the discretization and finite volume effects, and these approximations must be removed, must be studied in order to make contact with the real world. But in principle, this provides us with an ab initio method to quantify
so a lot
QCD
of this
effects,
is very,
and it has
very
been
technical.
used. There's a
You
long
don't really
history of
need
its
to
use
understand
for
it, but
simple
these are the
hadronic
methods that
quantities
people are
where we
using
have results
to
with
try
some percent
to
precision already obtained. So it
improve our
does require
theoretical
large-scale
predictions
computational
for the muon
resources,
magnetic
but
moment.
it also allows for an entirely standard model theory-based evaluation
They're quite
of this
technical and very
contribution.
field specific.
The current state
If you're not
of
following this
lattice
bit
HVP
perfectly,
calculations,
you won't miss anything.
they come in with about 2% error, so still larger than the data-driven evaluations. There are about a half a dozen lattice collaboration who are working on this with multi-year projects. These calculations are very much ongoing and will be improved in the timescale of the experiment. The light-by-light contribution is currently estimated with a 45% error from lattice, from a pure lattice calculation. The first completed one was produced in 2019. Hot off the press, there is now a new complete calculation by the Mainz group, which was posted on arXiv today. Here's the arXiv number for this calculation. It is completely
summary of this slide.
With
a lot of
previous
people are working still
completely independent,
to increase
and we
our
can expect
theoretical accuracy for the magnetic moment of
as
the
well.
muon.
The lattice light-by-light and dispersive data-driven light-by-light evaluations are completely consistent with one another. This is what is shown here. Here I'm showing a comparison of different evaluations of the hadronic contribution from light-by-light to the anomalous magnetic moment.
And all of the calculations are pretty much in the same ballpark.
Point is the result that is quoted in the white paper. It is based on the data-driven dispersive evaluation, a combination of that together with the first lattice computation. And the points shown above the line are not included in the white paper. The older simple model estimates, including the Glasgow consensus, are consistent with this evaluation, but with errors that are not well understood. And here I'm also showing the new result, hot off the press, from the Mainz collaboration. The picture for the hadronic vacuum polarization is much more rich. There are many different evaluations, and I'm
so in this case,
showing
one of the contributions towards the theory
evaluations
has a little bit of tension between different groups with different methods. They're not too sure they agree on what the value is.
I'm taking the hadronic vacuum polarization evaluations from these different results. I'm adding to it the rest of the standard model contribution and comparing it to the Brookhaven experimental value. So that's what you see here. The black point, again, is the result that was quoted in our white paper, which is based on a combination of these two data-driven evaluations that use the same set of data. There are other evaluations that are not included in the white paper. I draw your attention to an evaluation over here that uses data-driven results with a piece of it calculated directly from the lattice, which is also consistent here. And these blue points over here show results from direct lattice QCD calculations without any data inputs. As you can see, the error bars are still very large. The filled points are used to provide average of lattice calculations of HVP that is also provided in the white paper. The unfilled points you see here came too late to be included in the white paper. They indicate
more
new
people in the chat
results
hoping for tension in the results so that they can work in theoretical physics. Majestic
shown
potato.
by the BMW
I'm sure you'll get there.
Which came out in February of
hopefully we
last
can get you
year.
some new physics
what I'm
to
showing
think on
here
today.
is the result as it will appear in a publication tomorrow, as I understand. You see that this result has errors that are much smaller. They are actually reached the percent level. They're also in mild tension with data-driven results, but at 2 standard deviations, this being the first sub-percent precision calculation, needs further scrutiny, especially also because the errors are dominated by estimating the effects
This was
of the
usually the time
approximations
when
that are
I was at
employed.
CERN that I started to drift away. But
So let me now
I'll stay alert for you
back on the
guys.
standard model result. Here again, I'm repeating the results that go into the white paper that are used in the white paper evaluation, which produce a 3.7 sigma tension with the Brookhaven measurement. And for comparison, I'm showing the lattice result, the lattice average from the white paper as well. So this results in a standard model prediction that is shown over here with an error of 43 in the last 2 digits. With that in hand, let me now provide you a quick summary. As I said, the QED and weak contributions are already known precisely enough. We don't need to add anything more. The hadronic vacuum polarization has a relative error of 0.6% and weighs in at 0.37 parts per million on the
QED
total.
and weak
These
is easy
results
to calculate.
will improve
Often
with better both
anything to do
theoretical
with
calculations
quarks,
and better
hadronic,
experiments.
is hard to
and there's
calculate.
also been a huge amount of progress on the hadronic light, which is now for the first time fully quantified. And we already see the recent improvement that is coming here. I would be remiss if I didn't also acknowledge all the people who made this work possible. We've had 6 workshops. Here are photos from these 6 workshops. I'm extremely grateful to all of my colleagues and collaborators on the Muon g-2 theory initiative coming together as they have. And of course, we've also had quite a bit of funding. So I leave you with an outlook, with a standard model prediction, with a rosy outlook. The work of the Muon g-2 theory initiative will continue. We will see improved standard model evaluations in the coming year. So on the theory side, the next few years will be very exciting. And with that, I think it is time that we hear about the experimental measurement.
So just to do a very quick summary of that, and I'm getting a little bit worried that they're talking about making things more accurate, because that maybe suggests the results aren't as stunning as they might be, or maybe it doesn't. Maybe it suggests the opposite. So to sum up this talk, this was telling us how we can calculate what we expect the magnetic moment of the muon to be. Lots of people working on this. We've got a very good idea of what the value should be. There's some areas of contributions to it that need a little bit more work, particularly when it comes to quarks contributing, but we have a good value. And that value hasn't changed much over the last 20 years. And we therefore have this measurement. So here's our theoretical prediction. We have a measurement which is still 3.5 sigma away from it. And we have that tension still remains. So we're going to see what the new experimental measurement comes up with and whether it's still in tension.
Thank you very much.
Okay, thank you very much, Aida.
So a nice introduction and re-going over the theory and what the value,
Chris,
quote unquote,
I'm really,
should be.
really excited for your talk. I don't know what numbers you're going to show.
Well, apparently they don't even know inside Fermilab what the results
are
going
going
to
in
be,
just a moment,
which is interesting.
Get this started for everybody.
So maybe my prediction that she was hushing things over is not fair.
Hello, everybody. It's very exciting to be here. My name is Chris Pauly. I'm a scientist at Fermilab. I've had the honor of serving as a co-spokesperson, one of several that have served in the position over the years that we've been building this experiment, and I'm happy to represent the collaboration today. What I'd like to point out really quickly is that we are now at capacity on this webinar because we have a very broad range of people interested in this first result. We have many physicists, we have members of the public, and at this point, the webinar is saturated with 5,000 attendees. So if your friends are having trouble finding it, please redirect them to the YouTube live stream. You can find that link from the Fermilab
homepage.
We're in,
guys, don't worry. I won't refresh
so with that,
in this case.
We'll get started. I hope you're as excited as we are. I thought it might be fun to start by showing you guys a picture of what this idea looked like many years ago. And what I want to draw your attention to is the date in the lower left. This is actually the first time this concept was presented in a talk at Fermilab. And you can see in a few days, it will have been 9 years ago. In fact, the whole effort started several years prior to that. And it's really been an enormous effort. Well over 200 scientists, engineers, technicians, People from 40 different institutions across 7 countries have contributed. So for us, this is really our equivalent of a Mars rover landing moment, if you all tuned in for that exciting moment a few weeks ago. So what you see here is a rendering of this idea that emerged about 10 years ago. And that idea was to take the accelerator complex at Fermilab, the part of it that had formerly been used to make antimatter beams, antiproton beams for the Tevatron, and convert it into a source capable of making a high intensity muon beam. Fast forwarding until today, and you can see how that rendering has become a reality. In the foreground, you can see 3 buildings kind of in a triangular array there. That's the last stage of the accelerator complex, the part where the antiprotons used to be stored, that we now use to make this intense beam of subatomic particles called the muon. In the background, you can see 2 experimental halls. The one on the right is where the Muon G-2 experiment is housed that we'll be talking about today. The one on the left is our sister experiment, Mu-E. And really what I want to emphasize is this result today is the first result in a decade-long string of results that will be emerging from this facility. So it's a very exciting time for us and for the program as a whole today. Okay, so because we have such a broad range of attendees, I thought it would be good to go back and just talk a little bit more about what a muon is. So muons are one of the fundamental building blocks of the Standard Model. You can see this picture on the left. This describes all the basic ingredients at nature's most fundamental level, the ones that particle physicists like to study, the ones that theorists like to try to understand how they come together to describe everything we see in the universe as it evolves. They're very similar to electrons. That's why it's drawn down there. That's why it's associated down there with the electron you see on the lower left. They have the same charge, they have the same spin properties, and they have a few important differences as well. First of all, they're 200 times heavier, and they're unstable. They only live for 2 millionths of a second. So you don't get very long to look at one or play with it once you've made it. And in fact, that's why we use an accelerator complex to generate them. You can't just go out and scoop up a clump of dirt and find a bunch of muons in it because they will have long decayed away. Now, they are constantly raining down on us from the atmosphere where they're newly generated in cosmic ray interactions, but we make a much more intense beam of them here at the laboratory. So, the property that we're particularly interested in on the Muon G-2 experiment is the magnetic moment of the muon.
So this is a really nice,
because the muons, like their cousins electrons, have spin and charge. You can think of them as little bar magnets. They actually generate their own internal magnetic field. Like a bar magnet, they feel a torque when you place them in a magnetic field, and that torque will cause the muon spin to precess around the magnetic field. Much like this analogy you see here with the gyroscope, if you've ever played with one, you know how it can rotate or precess around a gravitational field. It has a spin axis, but that spin axis itself can revolve. The rate that that revolution happens depends on 2 things: the strength of that internal magnet inside the muon and the strength of that external magnetic field that it's placed in. The strength of the magnetic field in our experiment, we've been looking at it both for electrons and muons for well over 100 years. It's told us a lot about fundamental physics. Moment of the muon. At the turn of the century, as you heard Aida describe, turn of the last century, the expectation you would have found from a classical physicist was that it would have a particular strength. We like to note that strength by this coefficient G, we call the G factor, and G would have been 1 in a classical theory. It was shown that with relativistic quantum mechanics that the expectation for G is actually 2. But as you can guess from the name of the experiment, Muon G-2, there's actually a little bit more to the story. In fact, you just heard from Aida all the contributions that can go into making G slightly different than 2. And the reason that is because muons, like other fundamental particles in the universe, are never truly alone. They're constantly surrounded by an entourage of other particles that blink in and out of existence. They appear for just a fleeting moment in time. And that means the muon doesn't really see the magnetic field it's in directly. It sees it through this forest of other particles, these friends that keep popping in and out of existence. What friends? It turns out all of them. All those particles in that Standard Model picture can fluctuate in and out of existence. And our theory friends work very hard to calculate what we expect that to change the magnetic moment.
Lots of contributions.
Exactly. And so you can see the number with the incredible precision that the theorists have calculated that Aida presented there. We're interested in the anomalous part of the magnetic moment. It's historically been called that because it's the part that G factor differs from 2. It's the interesting part, the part that has to do with all the particles that fluctuate in and out of the vacuum. And the reason we're interested in it is because it allows us basically a window into that universe where we can see the impact of all those fluctuating particles, not only the ones we know about, but also the ones we don't. What kind of particles are out there that we might not yet have discovered? Well, there's quite a few possibilities. After all, we're out to study the big picture questions of the universe, like what is the source for all the dark matter we see in the universe? When we look out, we see roughly 4 or 5 times the mass in the universe that we can account for with the visible matter that we know about. We don't really understand that. We could be swimming through a sea of particles right now, and the muon spin precession in a magnetic field can tell us something about if there's, friends we don't know about that have joined the party. Supersymmetry is another example. We've discovered the Higgs mass. You might remember that very exciting discovery from the field. To this day, we don't really understand why it's so light. There's theories out there that would help us describe why the mass of the Higgs came out what it was when it was discovered. And in fact, there might be more than one Higgs. There could be multiple of them. And these are the type of questions we'd like to answer. But of course, as an experimentalist, I have to say, what we're interested in is anything that can change this from the standard model prediction, because we don't know what other monsters might be lurking out there, appearing in the vacuum that have yet to be hypothesized or discovered directly elsewhere. The reason it becomes particularly interesting is because there was a hint of this kind of new physics that emerged 20 years ago at an experiment at Brookhaven National Lab. That's the last time that this anomalous magnetic moment of the muon, this A that is related to G that we like to talk about, that's the last time it was determined experimentally. And at that experiment, they found roughly a 3 sigma discrepancy with the standard model calculation of the time. Just to set the scale for that, we like to talk in sigma in science because it tells us how significant our findings are. And 3 sigma is something you would really only expect to happen about 3 in 1,000 times just by fluke. So it's starting to get pretty unlikely, but it doesn't quite meet the bar for discovery. We like to define 5 sigma to say we've confidently discovered new physics in the universe. Over the intervening years, you can see in this plot, what's shown is the theoretical prediction in the pink bands and how it's evolved in the 20 years since the Brookhaven experiment ended.
We've got better
you can see in the green bands the value that was found by the Brookhaven experiment. And you can see in the blue band where we're trying to take the Fermilab experiment at the end of the day. We would like to reduce that experimental uncertainty by a factor of 4, because really...
So just to pause 1 second and point out what's going on here. So the blue points show how the theory has advanced over time. So we've become better at predicting what the magnetic moment of the muon should be. And the red point is our current understanding. And because the errors on that theoretical prediction have got smaller over time, and this green point at the top has stayed the same because we haven't made a measurement for 20 years, the discrepancy in terms of significance between that result from 20 years ago and our model now has actually got bigger, even though we haven't taken any new measurements, but we have shrunk down our errors on theory. So we really have a growing and growing tension between this old result from Brookhaven and our best theoretical prediction of what the muon's magnetic moment should be.
The question is, in this white space in between where the theory has a prediction and where we determine the experimental value, what monsters might be lurking. This difference has intrigued physicists for many years.
The white space is like the no man's land between theory and
on the right.
experiment.
That's the number of citations per year from other scientists in the field trying to propose what could be causing this difference and expressing their general interest in this kind of this discrepancy. And so you see, it's really stood the test of time. So our goal was essentially to bring the container that was used to hold those muons from Brookhaven, because it's an exquisite device, upgrade the experiment in every way possible, and couple it to Fermilab's extremely powerful accelerator complex. And that way, we hope to reduce the overall error by this factor of 4 to 140 parts per billion. I should just say that's the unit we like to speak in, because it tells us how precisely these quantities are known. You saw earlier in the theory slide, the theory is known to 300. So you saw it back here. The theory is known to 368 parts per billion, so that's good for setting a scale to compare the experiment to. So our goal is to reduce the experimental error down to 140 parts per billion to get ahead of the theory, and that requires 20 times the muons to be produced than were used at the Brookhaven experiment. So we reduced the statistical error from 460 from that experiment to 100, and we need to control systematics at a similar level of 100 parts per billion, which represents doing it about 3 times better than at the Brookhaven experiment. For those of you that have followed the story over the years, you know there was a very interesting episode in our history when it came to try and get that device from Brookhaven to here. You can see the device as it was constructed at Brookhaven in the picture on the right here. And of course, the problem we had with it is it didn't come apart completely. It's got superconducting coils inside of it that you can't cut apart, you can't take apart in any way. And so therefore, we had to transport parts of it whole. And we transported it 3,200 miles, you see, by land and by sea. You can see those coils on the upper right picture mounted on a frame here. That frame was just to keep it rigid during transport. And you can see the ground transport and the bar being lifted on the barge in New York. The difficult part was on the Fermilab end. We had to transport through about 30 miles of Chicago suburbs. And you can see what the pictures look like as we rolled out onto the interstate, closing the interstate for a few hours on 2 separate evenings. It made for some incredible photo opportunities. Here you can see our ring passing in front of the St. Louis Arch. You can see it on the lower left as it came off the barge in Lamont, Illinois. You can see on the upper right where it arrived to a large crowd of onlookers
who really interesting history to this. I know Jason,
laboratory.
Who's
and then you can see this
Horizon in the
cloudscape
comments
on the lower right that
knows
emerged
a lot about this history
after the crowds had gone home.
Hopefully we'll chat about it tomorrow.
I want to point out that getting your barge stuck is not just a Suez Canal problem. Here you can see us trying to navigate one of the locks in Lamont. I'm happy to say we got our barge unstuck without any difficulties, and it continued on its way where we brought it to Fermilab, put it all back together, and made it work again. So here you can see an overview of the experiment. It no longer has the thermal insulation that you saw in the Brookhaven experiment. This is what the bare magnet looks like with the steel and the superconducting coils. We bring beam in through these orange magnets in the back. They bring in the muon beam. It circulates inside here. So just to recap, you can think of muons as little spinning tops with a magnetic moment. That spin causes them to precess in a magnetic field. And what we really need to determine is that precession rate to a very high precision to compare with the theory. So this is a cartoon of how that looks. The muon doesn't rotate quite as fast as it's shown here, but the muons enter, they rotate, and our goal is to measure that frequency very precisely. Let me say this talk goes back and forth. It gets a little more technical for the physicists on the line, and then we'll come back to things that are more accessible to the public. So bear with me, and I hope you enjoy it. So here's a part that starts to become a little technical. Why do we use a storage ring? So we inject bunches of muons, roughly 10,000 at a time we store inside this ring, and they're nearly 100% polarized, meaning all their little spins are pointed in the same direction. The rate that muon spin rotates with respect to the frequency that the muons go around and around is given by this difference frequency. And the interesting thing you can see is this difference frequency we call omega A is proportional directly to the G factor minus 2/2. That's the anomalous part, the part we're really interested in. So if G were identically 2, this would be 0, and that spin and the momentum would forever stay locked together as the muon travels around. But to the extent G is slightly greater than 2, the muon spin.
So if we can measure this WA or omega A, we know Q, the charge of the muon. We know the mass of the muon. We can measure the magnetic field in our storage ring very, very accurately and map it very, very accurately. The only thing remaining in this equation would be our G mu that we're looking to calculate. So if we can measure the precession frequency very, very accurately in our experiment, and map the magnetic field in our experiment very, very accurately, all the other stuff are fundamental constants and the thing that we're looking to measure.
It goes a little faster and gets out ahead. And that's what we need to determine. We determine that by looking at the muons decay products. The muons decay into positrons in our ring. They come spiraling inward, and we detect those positrons with detectors that are arrayed around the inside of the ring. You can see what those detectors look like here. You can see there's a picture, there's a circle of one of them here. There's a total of 24 of them. You can see what one of them looks like rendered here. And inside of them, there are these beautiful lead fluoride crystals. So the way we actually see that precession frequency is when the muon spin is aligned with the momentum, it has a different energy spectrum than when it's pointing the opposite direction of the momentum. And here in this cartoon on the right, you can see theoretically what that looks like as the energy spectrum fluctuates up and down and up and down.
So we can get an idea of the current spin of the muons as they go around by looking at the products that the muon decays into, these positrons, and looking at the direction and the energy with which they're emitted. And that gives us the spin direction of the muon at a particular point. And if we take that at a load of points around the ring, we can see how that spin of the muon is changing, how it's precessing, and we can work out the rate that it's precessing.
As the muon spin is aligned and anti-aligned with its momentum.
So very clever.
Its direction it's traveling. So by simply drawing a cut on that plot and looking at the number of events that are above that cut, we can make the famous g-2 wiggle plot, which plots the number of decay positrons we see as a function of time. And you can see they're going away exponentially because of the muon lifetime. As I said, they don't live very long. And then they're wiggling due to this energy spectrum. The whole point of the experiment is because this difference frequency is directly sensitive to A mu, it makes you 800 times more sensitive than an experiment at rest, which would measure G directly. And that's why we do this whole experiment in the storage ring. That also comes with complications. We need to provide an electric field in addition to the magnetic field to keep the muons from just spiraling up and spiraling down and getting lost. That electric field makes the equation a little more complicated because it can cause the muon spin itself to precess as well. So we have to apply an electric field correction. But first we play a trick, because you can see there's a coefficient in front of this electric field term, and it depends on the anomalous magnetic moment and the relativistic gamma, which is essentially how fast the muons are traveling. If you choose muons that are traveling at 99.94% of the speed of light, that coefficient goes to 0 to first order. And therefore, we need to know the electric field environment with a much smaller precision, and that enables us to do the experiment at the precision we require. In addition, because the muons aren't always traveling perfectly perpendicular to the magnetic field, because they swim and they breathe, they're in sync.
So when we fire muons around very, very fast, this value gamma, which has to do with relativity, becomes very, very large. And therefore, this contribution becomes 1 over a very large number squared. So it becomes 1 over a large number, which is 0. It disappears. So we don't need to know the electric field we apply in our experiment very well, because it's a tiny, tiny contribution, because the muons are whizzing around very fast.
At first, so that breathing motion and swimming motion we refer to as coherent betatron oscillations. But just the fact that every individual muon is moving up and down in the storage ring leads to a correction we call the pitch correction. So these effects must be accounted for both in the detector acceptance and in how they perturb the precession frequency itself. So if you look at this equation a little more carefully, you can see in addition to having to determine omega A, if we want to extract the anomalous part of the magnetic moment, we also need to know the magnetic field and the charge to mass ratio of the muons. We use nuclear magnetic resonance to find the magnetic field in terms of the precession frequency of protons that we use to monitor the field. So you can think of it as a co-magnetometer. What we're really doing here is measuring the rate that the muon spin precesses relative to that of protons in a water sample. To do that, we have 378 fixed probes arranged above and below the volume where the muons live. They monitor the field 24/7. Every 3 days, we pull out this beautiful NMR trolley. It rides on rails, travels around in this vacuum chamber, that, as you see pictured here in cross-section, mapping the field where the muons actually live as they're circulating. And you can see those maps beautifully drawn below. In the end, this trolley has to be cross-referenced to an absolute standard. And so we do that through a series of a number of probes. We have a cylindrical probe that we use for the absolute calibration. That, in turn, has been cross-calibrated with this spherical probe that for many years has been used as a standard in our field. It was used at the muonium hyperfine experiments at LAMP. It was used at the Brookhaven experiment. So this one probe travels through, continually allowing us to cross-calibrate experiments from decades gone by. Most recently, one of our collaborators has pioneered the use of helium-3, which gives us yet an independent way to do the absolute calibration and they agree extraordinarily well to, part per billion level using helium-3. The equation gets a little more complicated. I won't go into this in detail, but what's important to note is that on the left, this is what we have to determine: the precession frequency of the muons relative to the protons in our water samples that we use to measure to determine the magnetic field. We also need to know the charge to mass ratio and a bunch of other ratios that we need to calibrate the water sample. So the plot in the red, the part in the red here, you can simply look up in CODATA. And the important thing to note is that all of the largest individual uncertainty for the things we require from other experiments is about 22 parts per billion. Just to remind you that relative to what we're trying to do is 140 parts per billion overall. So from an analysis big picture, we need to determine this anomalous precession frequency. We need to determine the average magnetic field that the muons are living in. And then we need to convolve that muon field with where the muons actually exist inside this volume. And so you can see this image on the lower right shows you where the muons actually populate the storage ring in the.
So if you want to understand the magnetic moment, you need to map the B field, the magnetic field in your experiment very, very accurately. And then you need to get this precession frequency very, very accurately. And if you know the precession frequency and you know the magnetic field that your muon has been subjected to, then to see the results that you get, the magnetic moment must be of a particular value. So you measure that precession frequency and the B field, the magnetic field in your experiment. There can only be one value, obviously with an error on it, that gives you the output, the results, the decay results that you expect. So you can get at that magnetic moment of the muon.
The run one experiment, the first run of the experiment that we're talking about today. We imaged that distribution using a beautiful set of in-vacuum straw trackers. You can see how they look in the picture on the right from a muon's eye view, and you can see the plot that shows decay positrons interacting with the trackers on their way into a calorimeter. The trackers give us much more information also. They really time resolve the image of the muon beam and the storage gap through the decay positrons. So you can see here those coherent betatron oscillations as the beam swims and breathes and all the motion associated with it. Okay, so just like there's more to doing that translation that requires some other constants, there's more that we have to do on our end. So just focusing on this ratio that we need to determine, the precession frequency to the determination of the magnetic field, there's a bunch of additional ingredients. So first of all, there's corrections because of the E field and the pitch that we mentioned earlier. We have other corrections due to the fact that muons might be lost from the storage ring, and one we call the phase acceptance that I'll come back to. You have to do the eventual field calibration, absolutely. And then
So a lot of these are very small corrections due to the real world, essentially. An experiment isn't perfect, won't be perfectly circular. We need to apply electric fields to keep the muons in. There'll be tiny errors in the way that we measure time, in the way that we measure the magnetic fields. So you don't need to understand exactly how they do all these things, but just realize that in the real world, things aren't perfectly circular. Measuring magnetic fields isn't perfectly accurate. All of these things will have little errors on them, and they feed forward into an error on that precession frequency.
We also worry about field transients, times when there's a perturbation to the field while the muons are in the storage ring that we wouldn't see with our NMR systems that average over time or only make a measurement every 3 days. Every one of these terms has been studied in extraordinary detail over the last year. How much detail, you might ask? Well, these are the systematic uncertainties that have all been studied to exquisite detail. And I think the takeaway point from the slide is really, if you start looking at these numbers, you can see most of them are much smaller than 20 part per billion. So they're much smaller than our eventual goal, and quite a bit smaller than the statistical precision we have on this run result. They don't really enter the controversy. As if that's not enough, those are just the uncertainties on the numerator. There's also a whole set of systematic analysis that has to be done to carefully understand the denominator in those terms. And I know because everybody is bored during COVID times and you've run out of things to watch on Netflix. I thought for the rest of the day, we just sort of step through these numbers one at a time. So, okay, clearly we can't do that. So instead, we'll talk about a few of them. But for all the physicists on the line that really want to understand, the details, I'm happy to say we have 4 articles hitting the archive today. There's the PhysRev letter announcing the result, and then there's 3 supporting articles describing how the beam impacts the result, how the magnetic field is determined, and how the precession frequency is extracted. This was a first for Physical Review to co-publish 4 results on the same day. These are working through the journal. The PRL is already available, and we're aiming to get the rest of these up. I think 2 of the 3 of them will be posted tonight. They're all going to be open access. I think 1 might be in a final proofing stage. So all these are either available or shortly available to you.
Some
and
bedtime
they're all
reading
on the
for me.
archive as of this evening. Also, we have 2 more seminars in this joint experimental and theory seminar series. You can tune into those later in April, where Saskia Charity is going to talk about the magnetic field and Lawrence Gibbons is going to go into detail on the precession frequency. So let me just skip to the final uncertainties from run 1. This is the table of all of those uncertainties, categorized largely in the terms that you saw in the equation on the prior page. And the thing to point out is with this run 1 result, we've achieved a 462 part per billion overall error. So we're on our way to our eventual experimental goal. 434 parts per billion of that is statistical, while 157 of that is systematic, and 25 comes from those co-data inputs I mentioned earlier. So the results from run 1 are vastly dominated by statistical error. And at 157 parts per billion, that systematic error is about half of what the Brookhaven experiment achieved, but we're not quite to our 100 part per billion goal yet. So I'll just highlight 2 of the systematics here. And for the public members of the public audience out there, this is going to get a little detail on the next couple of slides, but then we'll come back and discuss the result,
So again, very technical, very sort of esoteric stuff, really. Some of the errors that mean that you can't get the exact value of the precession frequency and therefore the exact value of the muon magnetic moment. Real world problems with running a complicated experiment, which we're going to talk a little bit about now. But if you don't follow the exact details, it's not too important.
I know you're interested to see also. Okay, so you can see in this table of systematic errors, the 2 largest ones come from B sub Q, which are quad transients, and C, the correction due to phase acceptance at 92 parts per billion and 75 parts per billion. It's interesting to note that if you just removed those 2 errors by themselves, we would be at 100 parts per billion, already attaining the goal for the systematic error for the experiment. We won't remove them completely, but we will address them in large part, as you'll see in the next couple of slides. So first of all, starting with the quad transients. So recall, we need this electric field to keep the muons vertically confined. The quadrupole system that provides that electric field is pulsed. That pulsing induces mechanical vibrations, and those mechanical vibrations of the conductor in a magnetic field can momentarily perturb the magnetic field just after the muons have been injected. This was quite a task to assess this error. We really had to go back and build special NMR probes to map this effect in the region where the muons live. So when people say, hey, it's been 2 years since you guys finished taking that data, what's the holdup? This is the kind of thing that you have to do very carefully. We needed to go back, design new equipment, make very detailed measurements to make sure that this correction was understood. At the end of the day, it turned out to be very small. 17 parts per billion were the correction. But you can see the full extent of the oscillation was as large as 303 or 400 parts per billion, but it were saved because we really only care about that perturbation when the muons live in the ring. These little gray bands show the times when we inject muons into the ring and the time that they're living and circulating around. This zooms in and shows you one of them. So by the time you average over all these 8 pulses during the times we actually care about, that's why this becomes so small. The uncertainty on it is actually larger. It's 92 parts per billion, and that's because it's dominated by not yet having a complete map at the time that we finished the analysis for this run 1 result. Since that time, we've taken much more complete maps, and we expect this uncertainty to be reduced by another factor of 2 or 3 for our run 2 and beyond. Coming to the other large one on the table, we call it the phase acceptance error. And we have to come back and think for a moment about this diagram or this plot on the left that can simply be described as an exponential decay of the muon and this oscillation, this cosine sinusoidal sort of variation that we're trying to see the muon spin precession with. The actual fit function we use is vastly more complicated. It has to be to account for all the beam motion, but this one's good for conceptual purposes. So the question becomes, this phase is determined by how did the muon spin point when it was first injected into the storage ring relative to the momentum? And ideally that would be constant in time because it's determined out injection. But what if some of the muons with a different phase are lost compared to other ones? There's ways where the population can still change. And if you take that phase and suddenly make it time dependent, expand it in a Taylor series expansion and recollect the terms, you can see the phi prime here could shift omega A in a way that you could never fit for it and determine it from the fit function. It would just be hidden from you in the fit. So that's the important sort of overall effect that we worry about anything that might change the
very
phase,
technical
very
details,
carefully.
basically saying that
So for this particular
small errors on the
the decay positrons we detect carry a particular phase.
Or determine from the experiment.
That phase depends on where exactly in the volume the muon decayed in X and Y and the energy of its parent muon. Which isn't, and this shows a map of sort of that phase depending on where the positron was born in the storage volume. It's not a big issue if the muon distribution remains stable over the long term, not the short-term oscillations we're talking about for coherent beta oscillations, but over the long term while we're observing the muons, we need that average to be stable. Unfortunately, in run one, we had an equipment failure where some of the high voltage resistors in that same quadrupole system we discussed, they died early on in the run in a way that we weren't able to replace them. And that led to a changing electric field. So the plot on the right shows the voltage, how it's supposed to come up in time in the black and the red dots here, and be on and stable before we start the measurement period with the muons. But for a subset of the quads, with this resistor problem, you can see the turn on time change dramatically. So this beam basically drifted down. You can see the plot of the position of the beam vertically here. And more importantly, the width of the beam change. And you can see because of the shape of this distribution, the width can really couple to a change in the phase. So that took quite a bit of detailed analysis. In the end, that was 158 part per billion correction with a 75 part per billion uncertainty. And because from run 2 and beyond, these resistors are fixed, we expect this result, this error will be reduced by a factor of 4 or 5. There's still some small things that can lead to it, but it will be largely under control. So with better maps of that transient effect, with the resistors fixed and a few other improvements that I'm not talking about today, we're really on track for the 100 part per billion systematic goal for run 2 and beyond. So with that, I have one final thing I want to bring up. In this equation, the thing I didn't talk about yet was this factor F clock. That's the frequency that our clock ticks along at. Tick, tick, tick. It's a precision timepiece. It's stable at the part per trillion level. So it's not in question that we know the frequency, we know the frequency of our clock very precisely. But the interesting thing about the clock is it's how we do a blind analysis, because we know this is a...
So for you guys out there listening, a blind analysis, this is something that we do in particle physics all the time. We don't look at the results or the preliminary results of our experiment, because if we look at the results and we find they're leaning in one direction or they're not very different from the standard model, we can fall into confirmation bias and we can lean towards changing our methods and changing our analysis techniques slightly to try to push them even further in that direction and towards a difference that we hope to see rather than one that exactly exists. So the preliminary results are often blinded, which means we don't look at them until the analysis techniques and the analysis methodology has been completely agreed. Only then do we do the final analysis and get that final result, and then we don't go back and change the analysis for that result, because otherwise we could be biasing ourselves and falling into confirmation bias. So in this case, it looks like, as usual in particle physics experiment, the final result of that oscillation frequency is not known by anyone until the very, very end.
Such an exciting result. And whether it lands on the standard model theory or whether it confirms the Brookhaven is extremely interesting. And as scientists, we try to avoid our internal bias by what we think the exciting result might be. And so to do that, we blind this frequency. We have the clock ticking along at a frequency that nobody on the experiment knows. It's a little bit like if you had a watch and your watch ran fast. You could never really tell what time of day it was. Just like that, we don't know what frequency our clock ticks at. It lives behind a locked cabinet that you see here, and two members who aren't in the collaboration, members from the Fermilab Directorate, come every week just to check and make sure that it's all in good shape. They keep the number in a secret envelope, and they keep it there until the analysis is complete and ready to be revealed. So with that, I want to ask Aida specifically, since she's been waiting anxiously to see this result and has managed to keep herself blind through all the times we practiced it and discussed it. Are you ready for us to unblind?
So even the people at Fermilab don't know what the results are. For example, Aida, who was doing the theory introduction, don't even know the results. So they're just as excited as we are.
Oh, Chris, I am so ready, please.
That's the same question that we asked over 200 of our collaborators. They unanimously agreed that it was time to unblind. After 2 years of detailed work, they were very confident that their job had been well done. And so they said, let's open the envelopes where the hidden frequencies are kept and see what we got. This all took place on February 25th. And between February 25th and today, nothing has changed. The only thing that we really worked on was getting those archive submissions ready so we could go public today with the announcement and have all those hit the archive at the same time. And kudos to these 170 people for keeping the secret. I have to say, I haven't heard it leak substantially anywhere, which is really quite amazing. So good job, guys. Okay, so thanks to the miracles of COVID times, this whole unblinding procedure had to be done on Zoom, as you can see here, which meant we also had the opportunity to record it. And I want to remind you, this is our Mars rover moment. 10 years, thousands of people, years of effort, suddenly in one moment being revealed to the collaboration. And lucky for you guys, you get to see that moment because we recorded it.
Put it up on the screen.
What you see here is the frequency on the clock on the lower number.
39997844. Same number. Yay!
Yep. It's the same number.
And this is what we get.
So once that unblinding frequency is known, that final little bit is known, you can finally calculate the results that are coming out of the experiment.
Whoa! Wow!
Oh,
Wow. Oh my God.
we confirm page 21.
All right. Isn't that fantastic? I can't tell you what this moment was like for the collaboration that had worked so hard for this result. And you can see it really comes down to something as trivial as typing the number in, you see highlighted in the ellipse there, and watching the number appear on the plot. So let's just step through real quick and go through the numbers on that plot. So first of all, this is the Brookhaven value. It's been updated for all the most recent values of code data, which have changed ever so slightly since the initial publication. The important part is that with a larger collaboration, largely new people, there's a few old people like me who were graduate students or were PIs on the experiment at Brookhaven, but with a larger collaboration, with a higher purity beam, with much more advanced instrumentation, we reused the same container, but we made its magnetic field 3 times more uniform than it ever was at Brookhaven, and much more powerful simulations.
So here we go. For Jason asked a good question, Horizon, in the chat about how can this be more accurate if it's the same experiment which has just been moved to somewhere else? Well, it seems like bringing it to Fermilab allowed a much more accurate determination of the magnetic field in the experiment, a much higher purity beam, more advanced instrumentation for looking at that B field. If you have a better map of the magnetic field, you can get a better evaluation of the magnetic moment. So that's the answer to that question that came in the chat.
In all that work, we never found anything that would have changed the Brookhaven result. So that's reassuring. So now we can ask, what about a whole independent set of data from Fermilab? What does it have to say? You can see there's the result from the first run of the G-2 experiment at Fermilab. It's slightly to the left, but you can see it has a 15% smaller error than Brookhaven. And these little tick marks on here show you how large the statistical errors are on both experiments. And you can see they're both really dominated by statistics. The fact that they're in good agreement means that it's safe to combine them.
Wow. So the results from 20 years ago from Brookhaven and the result from the first lab of G-2 at Fermilab seem to strongly agree. So that tension is going to remain by the look of it.
And you can see the combined value here. Quite interestingly, the combined value has an error of 350 parts per billion. If you go back historically at Brookhaven and look at the goal from the technical design report of Brookhaven, that was our goal then. So it only took 20 years. And here we are with a world average at 350 parts per billion using this beautiful container. Of course, the interesting part is...
So, of course, we combine those two results, the old 20-year-old result and now's result, and we get a new result, which is an average of the two, with smaller errors because we're combining the statistics of them both.
Compared to the theory prediction. Here you can see the prediction from AIDA. The individual tensions between Brookhaven is 3.7 sigma. We're at 3.3 sigma due to our small shift to the left, but our slightly smaller error bar. And overall, the tension with the standard model has grown to 4.2 sigma. Just to give you a sense of scale.
So to give you a little bit of a rundown of what we see here, the result that we have from G-2 at Fermilab is closer to the standard model prediction than the 20-year-old result from Brookhaven. But because this new result is still far to the right of the standard model, 3.3 sigma, when you combine them, you're even more sure that the results from Brookhaven and Fermilab tell you that the magnetic moment of the muon is not consistent with the theory prediction of the standard model. That's our purple result here. So we've actually moved further away and we have an even greater tension of about 4.2 sigma. That's what, 1 in maybe 100,000 or something. I'll have to check what 4 sigma is. But that is a very strong tension now between the standard model prediction of the magnetic moment of the muon and the experimentally measured value, which is starting really to lean towards the idea that there might be some new physics and some new particles hiding out there that are changing the magnetic moment of the muon. In particle physics, we want to get that up to 5 sigma, but this is highly indicative of potential new physics. It's not a proof. We don't have enough yet. We haven't got to 5 sigma, but it's very indicative.
The probability of that happening by chance is about 1 in 40,000. So we can say
100,000, I wasn't far off.
There must be something contributing to this white space. There must be something that explains such an unlikely result. Okay, so in conclusion, we've determined the anomalous magnetic moment of muon to an unprecedented 460 parts per billion. Our run 1 result is really just a small fraction of our data, but it's already surpassing the errors from the Brookhaven experiment. And after 20 years of people wondering about this mystery from Brookhaven, the headlining news here is that we confirmed the Brookhaven experimental results. So,
exactly right. So skimmed over that quite quickly, but this new set of data has confirmed those 20-year-old Brookhaven results. And because we have more statistics, double or more statistics, we can be more certain that we have a tension between the standard model prediction of what the magnetic moment of the muon should be and what we're seeing. So we can be far more confident now at the 4 sigma level about 1 in 40,000 chance that it's just a fluke, that we have some new physics on board. Very, very interesting. Very, very big result. Very, very powerful result. Very intriguing result, which, Chris hasn't got as excited about as I thought he might. Very, very interesting result.
As far as an outlook, I just want to remind you again, this is a plot of our data accumulation versus time. What we presented today are the results from run 1. And you can see plotted here the results from run.
Much more data to come means much more statistics, means those error bars will start to shrink. And even if that gap between the two results doesn't change, if the error bars get smaller, the significance of that difference will get better, hopefully up towards the 5 sigma level. So we can definitely say there's a difference between experiment and the standard model.
the data we've acquired in run 2 and run 3, and run 4 is actually in progress as we speak. Run 2 and run 3, the data analysis is underway. We're expecting to publish results from those data sets of order a year by next summer or so. And that will reduce the experimental uncertainty by another factor of 2. The overall goal of the experiment is to continue collecting data to achieve that overall error reduction of a factor of 4, which you see in our systematics are on track to be commensurate with. So again, the run 2, 3 analysis is in progress, and this is run 4 has started, and we plan to take a lot more data. Okay, I just want to take a moment, first of all, to thank the agencies and to you for all the support that you provided for basic sciences. We couldn't do this if people weren't passionate about trying to understand the fundamental basics of the universe. And you can see in the United States, we're funded by the Department of Energy and the National Science Foundation, and we have a whole host of international agencies that contribute to the effort. I want to also point out that we're a large collaboration. We have many collaborators all over the world who would love to provide a more detailed seminar, colloquium, public lecture in a smaller venue where you can really have a discussion and ask questions in an open forum. So we'd invite you to contact us for a talk. There's a URL here you can type in, or you can use the QR code. And once again, thank you very much.
And there's the important result, a huge tension between the standard model and the experimental value that we're seeing at Fermilab.
Thank you very much, Chris and Aida, for those excellent presentations. What an exciting result and an impressive body of work from the theoretical community, the Muon g-2 experimental collaboration,
This
and also
guy's
the
definitely
Fermilab
on the old
Accelerator
cue
division
cards.
that produced all those billions of muons to make this result possible. Joining Professor Alcadra and Dr. Polly for our question and answer session is Dr. Graziano Benenzoni, a physicist at the Italian National Institute for Nuclear Physics, PISA, and co-spokesperson of the Muon g-2 experiment. Welcome, Graziano, and congratulations on this exciting result. Members of the media are reminded that there will be a press conference at the top of the hour. We actually reached our limit of 5,000 participants in the Zoom session, and of course, many more connected to this presentation through YouTube. This entire presentation will be available on the Fermilab YouTube channel. We will also make the slides available on the website as well. We've received, I think it's above 60 questions now, and they continue to pour in, which is absolutely fantastic. So let's see if we can get through as many as we can in the time available.
So it looks like we're going to have a little bit of a question and answer session. If you have any questions that you want to ask me in the chat, I will endeavour to answer them as well. Otherwise, we'll look at some of the questions and answers that are coming through from the public to Fermilab.
Started with taking some of the questions. Let me direct the first question to Aida. A couple of questions actually related to the theoretical calculation. The first question we had was maybe a question about the clarification on what you presented as WP20, which I think was white paper. Could you just clarify exactly what that is with respect to the standard model?
That is the standard model prediction.
Okay.
So that is our best knowledge of what the standard model has to say about the anomalous magnetic moment of the muon.
Thank you. And you mentioned in your presentation the recent calculation of the g-2 hadronic contribution from the BMW collaboration, and we received several questions regarding that calculation. It's closer to the experimental result and is presented with smaller uncertainties. Could you say a few words about it and how it compares to this result and how it will be incorporated going forward?
So the lattice spacing, and it is not a smaller lattice spacing, and you might see results that are slightly different from what they quote. In fact, based on the same integrals that they have calculated, that have accumulated, and just changing the way their central value between the result that they quoted in February
actually are very correlated. Now, it is true that we use the same technique. And so if there's something fundamentally flawed in the technique, then that would, that could potentially be a problem that could explain the result. But, for 20 years, people have been thinking about this technique, and we haven't learned anything that's fundamentally incorrect with it. So.
Thanks, Chris. Let me bring Graziano into the conversation. Hi, Graziano. So
Hello?
this result is, as Chris presented, this result is statistics limited, that the uncertainty is dominated by the statistical uncertainty, and you plan to add additional data.
A little bit of lag in the stream. I'm just going to try and refresh it to see if we can excuse me, if we can get rid of that.
But the dynamics is the same for both. Good. So
somebody accidentally unblinded. How does that?
Or not with the unblinding.
So first of all, Graziano, is it really true that the collaboration didn't know this answer at all and then finally unblinded, and that's the number that you showed today? Is that really true?
No, we were joking. No, of course it was true, of course. And you can imagine, you can see already, you can see from the video that has been shown, I mean, how emotional was this moment. I mean, how people were really cutting the hair. I mean, just saying what will go. And yeah, I mean, we worked really hard because we wanted to establish some rules according to which how to proceed with the unblinding. So essentially, and this took, I will say, 6 months of the discussion within the collaborations. And at the end, we formalized the bylaws. And in our bylaws, we decide that whatever will be the results, we will publish. That's all. So we will not touch the results. So essentially, once that the results, once that the analysis were completed, so the blinded analysis they completed, and there were no outstanding issues, no outstanding questions, then the collaboration met together and decided, should we proceed with unblind or not? And we have a unanimously consensus to proceed with the unblinding. So there were really no question left, no issues left. And so we met on 25th of February, and okay, and what Chris was showing. So this was really a piece of history, which, by the way, was possible to record thanks to this, let's say, Zoom or online meeting. So it was really a very...
So this question basically just confirming that the results were completely blinded until these final results were given out over the last couple of days.
Very nice and emotional moment for us.
Thanks, Graziano. Chris, I want to continue a little bit more with blinding, because we had a few questions about what this means going forward now. For example, what you unblinded was this so-called run one data that you showed us today, and that was the result that we saw a few minutes ago. Is the data you'll be looking at going forward, is it still blinded? Is it with the same, can somebody accidentally unblind it? How does that all work? Could you explain that?
Yeah, fantastic question. It turns out there's not just one set of envelopes. There's a pair of envelopes that are generated for every run in that plot. The clock is changed in between the runs, changed by the same two people who aren't our collaborators. And then we start over again in a new year, once again with the timepiece that nobody knows how fast or how slow it's ticking. And so we'll be blind yet again in the subsequent publications.
Great, thank you. Aida, circling back to you, we got a couple of questions that asked about how the concept of lepton universality factors into your calculations. Could you, first of all, say what that is, and then second of all, say why that's an important question?
Very good. So lepton universality refers to the fact that in the standard model, the way that the electron couples to, say, the photon is exactly the same in which, that's the way in which, say, the muon couples to the photon. So the muon and the electron are the same part, have many of the same features. The only difference is that they have different masses, the muon being 200 times heavier. So that is the only thing that is different. And so that would affect, some kinematic effects, etc. But the dynamics is the same for both of these particles. So that's what we mean roughly by lepton universality. And so we can calculate the anomalous magnetic moment of the muon. and we can calculate the anomalous magnetic moment of the electron. The contributions from quantum fluctuations, from quantum corrections will be different because of the mass difference, but the dynamic contributions are the same. So we also have to evaluate the hadronic vacuum polarization and the hadronic light by light, for example. But because the electron's mass is 200 times lighter, those contributions are much further suppressed so that the electron ends up being really dominated by QED, even more so than, say, the muon. So testing that the muon and the electron and the tau lepton, that they act in the same way, is a good way in which we can test whether the standard model is correct. So there are some interesting new results coming out from the CERN experiment, LHCb, that is looking at ratios of certain decays into muons versus electrons. And there are some surprises there that would suggest violations of lepton universality. But standard model prediction, of course, is assuming, because it's assuming the standard model is assuming also lepton universality.
So basically, in a lot of these calculations, these theory calculations, we have to use standard model predictions. If there's breaking down of lepton universality, for example, that will change the theory prediction. So if that's observed, that will change our theoretical prediction for the value of the muon magnetic moment. So we have to keep an eye on experimental results elsewhere to be able to update the theoretical prediction for the magnetic moment of the muon. If things aren't running according to the standard model, we'll have to change our predictions.
In order to put non-universality effects into the theory, you have to, that would be beyond the standard model calculation. So if you want to know what are the contributions from a model that goes beyond the standard model where you have lepton universality violating effects, then you can compute those contributions also to the muon g-2 and the electron g-2, etc.
Thanks, Aida.
But it sounds like they haven't done it.
Let me bring this to you, because we had a number of questions related to kind of potential sources of what we would call new physics, or physics beyond the standard model with this result. And Aida was just talking a little bit about this idea of lepton universality, that's something we had kind of assumed was true. You're welcome to speculate, but that's not my main question. If you want to speculate on what you think might explain this disagreement between the calculation and the measurements, you're welcome to speculate. But actually, what I'd like to hear a little bit about from you is, how do you see things evolving in terms of, for example, potential explanations? How will those arise, and how will they be tested, kind of in a more broad sense?
Okay, yeah, that's a great question. So maybe I'll start with my own take on the lepton universality and go from there, because I do think that is one of the extremely interesting questions of our time. You saw that table with all the standard model particles in it, all the basic ingredients that we know about, and we've known for a long time that they like to array themselves in these groups of three. As physicists, as scientists, we try to understand, why is the universe the way it is? How did it all evolve? How did it come about? And we really just don't have any understanding of why these leptons and the quarks arrange themselves in these families of three. So for me, that's a very basic question. That's what when we say lepton universality, that's what we're talking about. And so anytime you can find something that sort of differs between a muon and an electron, or a tau and a muon, that's very exciting, because maybe that's the first hint of something that will eventually lead to a theory that explains to us, why does the universe seem to prefer these three generations? That by itself is a very exciting question, and what physics model that we haven't thought of yet, or maybe we have thought of, describes that. That will be very interesting to know someday, but the fact that we have these three generations and don't understand why is itself a mystery. And for people who pay attention to this kind of news, just a couple of weeks ago, there were results released from the LHCb experiment. There's a number of very interesting hints out there where other experiments are starting to see signs that maybe muons don't act like you expect relative to their electron and tau cousins. So that's starting to become very exciting. you can look up a table of those and you can find that, there's a number of them that are 2, even starting to push 3 sigma now. G-2 now will be the first that rises to this sort of 4 sigma threshold. And of course, we're just getting started. So I would say that part's very exciting. And of course, there's other proposals out there in the future for how we might go about making more dedicated tests of lepton universality. So the way we hope this works out in the end is we get some very solid evidence of numbers that, disagree so dramatically with the standard model that there has to be an explanation. And then once we have a theoretical model that predicts them, we can compare them. And much like when we first discovered that the G factor was not 2, it differs by 0.1%, 2.002. People at the same time at first wouldn't know what that meant. But then you have Swinger that calculates, the fact that electrons can self-interact. And when he does the calculation, he gets 2.002. And, it's these kind of comparisons between calculations from models and theory that allow us to basically realize we've understood something fundamental. So that's my take.
Chris, thanks very much. We have not reached the end of our questions, but we have reached the end of our time. Let me thank our 3 panelists today: Aida El-Khadra, University of Illinois; Graziano Venanzoni, INFM Pisa; and Chris Pauly from Fermilab for excellent presentations and a really interesting Q&A. Congratulations to all the people who made these results possible. And let me also thank the governments and funding agencies from around the world who help provide the resources to make this work happen. Finally, thanks to all of you in the audience for joining us today. As exciting as this result is, the work continues, as you heard, and there is more data to analyze. We hope to see you again sometime very soon for more information as this story continues to unfold. Thank you again for joining us today. Goodbye.
So there you go, guys. That's the end of the seminar. Very, very interesting result. A 4 sigma, so 1 in 40,000 chance of this being a fluke, of this being such a high tension between the standard model prediction, the theoretical should be value of the magnetic moment of the muon, and what we actually observe from the experiment. So I'm going to keep an eye on this. Probably going to do a longer video on this, explaining all the implications of this, what might be going on, how the experiment found this. Hopefully get that out over the next couple of days. If you have any more questions, comments, I'll leave the chat open for a couple more minutes. If you want to fire off a question, do that now. I'll give you a couple of minutes to do that. Otherwise, I'm going to go and grab some dinner and digest these results along with that. So give you a couple of minutes. If you've got any comments, final questions, shoot them off in the chat. Otherwise, very, very interesting result. And I'll dive into it and explain it fully in a longer video very soon. So I'll leave that chat open a couple of minutes. And as I say, it's there for you to put anything you'd like. Thank you everyone for stopping by. I really appreciate it. And we do have a question. Does this mean the standard model is now wrong? From Samuel Keithley. Samuel, great name, by the way, obviously. Doesn't necessarily mean that it's wrong. We know that the standard model can't be complete because it doesn't explain certain phenomena like gravity, like dark matter. So we know in that sense it's wrong, just like all our models of the universe are wrong, but we're trying to make them less wrong as time goes by. Does it mean that the standard model prediction is inconsistent with this experiment? Not necessarily. There's only a 1 in 40,000 chance that this is a fluke result. So it strongly suggests that the standard model is quote unquote wrong. But we're not quite there yet. In particle physics, we're going to wait for some more data, try and get up to about that 1 in 10 million chance of it being a fluke before we make such a declarative statement. But this is very, very highly indicative that the standard model, for want of a better word, might be wrong. There really is a strong tension here between the standard model and the experimental value we're seeing. So wrong, quite a harsh word, but yes, we're very, very close to potentially being able to say that in this instance, the standard model is wrong, or at least is unable to predict the result that we're seeing. So with a little bit more data, we should be able to give you a yes on that, hopefully. Any more questions? Let's keep it open until 22. No problem, Samuel. You're very welcome. There's been some really good interest, some really good comments, some really good questions throughout the stream. So I really appreciate it. Majestic Potato saying excited for the future. Majestic saying that he wants to go into potentially a career in theoretical particle physics. I thought it was going to be a quiet time at the moment because we just obviously had the LHC firing up. Didn't find as many things as they were potentially hoping for. Obviously found the Higgs, which was the big ticket event, but supersymmetric particles didn't turn up. We're still struggling on dark matter. We didn't find the tiny black holes and such. A lot of these more exciting things, extra dimensions, didn't turn up. So a lot of the exciting things we were potentially hoping to find at the LHC didn't turn up. But over the last few weeks, with the results from LHCb, giving some hints at potential lepton or violations of lepton universality, along with results on similar phenomenon from all over the world recently. Now these results showing a strong tension between theory and experiment for the muon. Maybe it's becoming a little bit more of an exciting time in theoretical particle physics, and we don't need to be potentially so glum about the future. There's a lot of exciting hints out there of where new physics might reside, and a lot of interesting theoretical work still to be done in discovery and in precision physics. So it is a good time still, Majestic, to get involved, and I wish you great luck in getting involved with that. If you want to ask any questions about getting involved in particle physics, head over to the website badboyofscience.com. You got any questions, or I can help you out or give you any leads, I'm more than happy to do that. Shoot me an email. Any more comments? Questions or comments? Any more before I call it a day for today? Let's see if there's any more higher up in the chat. Give it another minute or so. Again, guys, thank you very much for stopping by. Obviously, you could have watched this on the Fermilab site. You could have watched it on some other people's sites. I'm really glad you came by to enjoy this unveiling with me. I hope you enjoyed some of the explanations, some of the grounding that I gave you, and I hope you'll come back to the channel in the future. It's been really fun and interesting going through this with you guys. And I think Majestic says it right when he says excited for the future. I'll keep an eye on this. As I say, I'll do a video over the next couple of days which explains this in more detail. So feel free to stop by and check that out. And always feel free to leave your comments, questions and suggestions under the video, and I will do my best to get back to you. I was always told particle physics was a dead end for a career in physics. Samuel, over the last couple of years, as I say, it looked like that might be the case. As I say, the LHC didn't come up with all the gold that people thought it was going to be. There was going to be, and it did seem. I remember Sabine Hossenfeld did a video about this being the death of particle physics. Essentially, we hadn't found as much as we thought we would. We only found the Higgs pretty much. Little bits of other things, and maybe this was the death of particle physics. Maybe we couldn't justify having another bigger, far more expensive experiment when we really hadn't found too much or many hints of things that would be easy to get to with a new experiment. With these results, it looks like things might be a little rosier, and hopefully there's there's some interesting places, for people like Majestic to get their teeth in and push forward on the new physics. So hopefully these tensions that we're seeing with the standard model will continue. And as I say, or as I said higher up in the chat, we can see the world burn, and hopefully we can move towards an even better understanding of the fundamental physics that underlie our universe. Because these hints tell us where to look, these cracks tell us where to look, and where these monsters, these new physics principles and particles might be hiding. Anyone else with a question, comment? Give it one more minute and then I'm off for my dinner. I see that Muonium thinks there's not going to be any life on Mars. I think was the old poll that was there. Yes, will perseverance find evidence for life on Mars? Is the old poll that was there from the last live stream. He doesn't think they'll find life on Mars. A skeptical man. Neither do I, to be honest. I hope they do, but I think they probably won't. Majestic Potato I'll give him the final word. Agreed with Samuel, but seeing the recent news keeps my hopes up again. I think that's a really nice place to finish. Again, we're finding these cracks in the standard model. There's lots of work to be done, and people like Majestic will hopefully be the people doing it, and we can finally get beyond the standard model. Guys, thank you for stopping by. Thank you for your brilliant comments and questions. And I hope to chat to you again soon. Take care.